Welcome to Sober Math. Those who took university physics or engineering may recall the forces of a ladder leaning against a wall or a falling ladder. What is often overlooked is a curve which bounds the falling ladder. Today I derived the formula for this curve and show how the falling ladder is related to a rolling wheel. I'll skip all that calculus and use only visual intuition and symmetry. In my related string art video, linked below, the sum of the intercepts didn't change. Today our constant is the length of the ladder. Up ahead I'm going to construct this detailed diagram, but we'll explore it in manageable pieces, and use simple trig to find relationships. Then finish with algebra. Are you ready? So picture a ladder as it leans against the wall. The floor, the wall, and the ladder itself form a right triangle with the ladder as a hypotenuse. If this ladder is falling, then an instant earlier it leans more steeply. Much like the string art video, we are now interested in where the ladder at two moments crosses itself, and the collection of all the crossing points is the curve that we are after. So we impose xy coordinates, call this angle theta, and now I draw a dotted line parallel to the green hypotenuse. Observe this angle. You may remember from geometry that it is equal to this one. We say that they are alternate interior angles to that blue line, called a transversal. Let's call this small angle delta theta. And so this angle is also delta theta. The y-axis also forms a transversal to the parallel lines, so these two orange angles are congruent, since they are corresponding angles, and so this orange angle is theta plus delta theta. So I'll define x0 and y0 as the lengths along its axis until the first ladder crosses, and these are symmetric. Here I define the small bits delta x and delta y and call the crossing point xl, yl. So the diagram is getting dense, but it will be okay, I promise. On the upper left, we impose this blue perpendicular segment of length little a. So for this tiny blue right triangle, the adjacent side is called delta a, and the remaining length of ladder from the intersection to the perpendicular segment, call it capital A. By symmetry, we repeat labeling on the lower right and use letter B this time. This little perpendicular segment has length little b, and this bit is delta b. And the remaining length of green ladder, I will call it capital B. And now to clean up. There, that's better, right? And the remaining quantities are all the tiny quantities. Again, consider the small quantities delta theta. If we make them even smaller, then the other small quantities shrink toward zero, like so. That's calculus. And it's these two stages of our falling ladder that are so extremely close in time that I'm really interested in. But my issue is that the triangles are either so thin or small that I can't really continue the discussion. So let's go back to the crude and exaggerated diagram. Oh, and the ladder has a length capital L at every instant. So going back to the original diagram and focus on the blue triangle, recall the definition of cosine is adjacent over hypotenuse, or cosine theta is y0 plus delta y all over L. The adjacent side is y0 plus delta y, but in calculus we can often ignore extremely tiny lengths like delta y, and so we can pretend it's y0. L squared is x0 squared plus y0 squared, and we solve for y0, and plug this in, and then put it aside. Now duplicate the little green triangle with the orange angle, which is theta plus delta theta. The cosine of theta plus delta theta is b over delta x, but delta theta is tiny, a tiny angle compared to theta, and we can just ignore it. Again, calculus. So we get cosine theta equals b over delta x. We combine two equations to get rid of the cosine, and then solve for b, and put it aside, and return to the diagram. And this time we focus on the big blue triangle. The sine of theta is x0 over L. It is also a over delta y. By the little blue triangle, we combine to get rid of sine and solve for a. Now check out the big green and blue triangles. We can write down the Pythagorean theorem twice. So now I did say that in calculus we can often ignore the little tiny lengths like delta x and delta y. But for now we can hold off because we'll combine these and the big stuff will cancel exactly and we will only be left with the tiny stuff. So we can combine them to get rid of L squared and then FOIL terms on both sides. Notice the x squareds and y squareds cancel. And now here we have delta x squared. So in calculus, it is super negligible. And so we can cross it out with impunity and do the same with the delta y squared. The 2's cancel and solve for delta y. Plug in delta y and multiply the x zeros. We want to get rid of these delta x's in each equation. So divide a by b. And rather than divide by a fraction, we multiply by its reciprocal. The delta x's cancel, and then the l's cancel. Now recall that y0 equals the square root of L squared minus x0 squared. When plugged into itself, we get this, which simplifies the a over b equation. And so back to the diagram. This thin blue triangle and thin green triangle are similar, so we can write down this proportionality. So little a over b equals cap a over b. And now go use the thin angle limit, and why not just go to the infinitely thin limit? Perfect. This blue triangle has base XL, and this green triangle has base x0 minus XL. They are similar, so we write down this proportionality. Cap A over cap B equals XL over the quantity x0 minus XL. And now we can finally put away that convoluted diagram and deduce our formula using algebra. Combine these and get rid of capital A and B, and combine these two to get rid of little a and b. And now, huzzah, everything is in terms of x and that constant capital L. So what can we make of this? Let's try and simplify. We cross multiply, then distribute, and we see these two terms cancel. What a nice little compact equation, right? Just like my string art video, everything is symmetric in x and y. Using symmetry, we get the corresponding y equation. Those are x0 cubed and y0 cubed. It would be nice if they were square instead, so that we can plug them into the Pythagorean theorem and get rid of them. But they aren't. So let's adapt them. Recall that anything cubed is just the same as that thing squared raised to the 3/2 power. So we can apply this form and get the x0 squared by itself by raising both sides to the 2/3 power, and then distribute the power of 2/3 to both factors. And now to do the same with the y counterpart. Now combine all three to get rid of x0 and y0 entirely. Almost done. So factor out that L to the 4/3 power and divide it out. And there it is, x to the 2/3 plus y to the 2/3 equals L to the 2/3. And that subscript L is vestigial, so we can just get rid of it. Does this discussion seem familiar? In that string art video, the square roots of our result can be written as 1/2 powers. And if those intercepts are measured in unit length, that string number is equivalent to the ladder length. And we can combine these two results to get x to the n plus y to the n equals L to the n, where n is 2/3 for the ladder curve and 1/2 for the string curve. So suppose you're moving furniture around a corner like this, and you want to know the length of the longest object that you can pass around the corner without bending it or twisting it. Then I claim that our ladder curve here is exactly the length of the longest one-dimensional object that'll fit around that corner. And so if you set x and y equal to w, that is the width of the corridor in this case. To keep it simple, I just said let the width be the same here and here. And then you plug and chug, and then eventually you get the length. The longest length is going to be equal to 2 to the 3/2 power. That's just 2 rad 2 times w, the width of the corridor. And that's, in hindsight, that makes sense if you just draw it right here. See, it's rad 2w, rad 2w, so that makes perfect sense.
If you want to keep a simple rule in mind, just say L cannot possibly be greater than 2.8. You can round it up to 3, like L is no greater than 3 times the width of the corridor. And it's even made worse if you make this thing thicker. So we also find that our ladder curve equation is obeyed by a wheel rolling within a loop like this. So if you have a piece of mud on a wheel, which is where the loop is 4 times the diameter of the wheel, then it will draw out this curve, which is exactly described by our ladder equation. And so that's called an asteroid without an E, asteroid involute. And it's formed by a wheel rolling within the loop without slipping.
In my next video, I intend to show a third curve, which is a hybrid between these two, and in so doing has a very strange formula. If you enjoyed this video, please like and subscribe, and stay tuned for the next one.